Seems like just yesterday I was still wearing snow boots. But no, we're almost at short season. It's almost May. So we have a few things in wrapping up the end of the class. Homework 7 is due this Friday. I now have put up the starter syntax. I hope that you find this relatively straightforward. It's meant to give you sort of an additional practice with interactions before we do homework 8, which is interactions in the context of longitudinal data. So you've been working on 7. Is it okay so far?
Last night I forgot to transfer the categorical variable to like the continuous way. So I spent a lot of time. The opponent variable. So this morning I converted that to like continuous way.
And it works better? Yeah, that's what I did. I made easy 0 and hard 1, and I pretended it was continuous when I built everything. I find that to be more straightforward than letting it do the coding, and it flips the 0 and the 1. Yeah. So, okay. Well, do you have questions about that? You good? Good so far? Okay. I also put up your last quiz. That is due next Tuesday. It's talking more conceptually about time-invariant predictors and what they're for. There's also a question on there that I have to explain. The last question is, what is your theme song? So have any of you been to a professional baseball game before? No? That's okay. You have?
Yeah.
So when someone goes up to bat, they typically play music, like to sort of like welcome that person, and each person usually gets to pick their own song. And I think of that as like your theme song. And so I'm asking you, like, if you were up to bat, like imagine yourself in some sort of high pressure situation where you need to like focus and get motivated, what would the song be that you want playing on the overhead while that was happening? It doesn't have to be English. You can pick any of your favorite songs that motivate you, but the key is that it has to be something to where the second the song starts, it's like bam, like, it's really cool. So that's what I want to know is what's your theme song? It's a question I ask every semester to try and get to know folks a little more. So and if you and I ask you to give me the artist and the title so I can look it up on YouTube. That way I can see what it is for myself. My theme songs in the past have been things like Motley Crue's "Kickstart My Heart." It's an old '80s hair band song. Shania Twain's "Man, I Feel Like a Woman." That's another one. Familiar?
Yes.
No? Yes? Okay. One year I had someone write down Christmas music, and I was like, no, that's incorrect. I'm sorry, that is no. There are no wrong answers except for that one. You cannot pick Christmas music. So I want to know what your theme song is. So I'll be looking for those after Tuesday. So we've decided, by the way, catching up for the folks who are just joining us, that I'm going to swap out next week's lecture on crossed models for multivariate longitudinal in an effort to give you exposure to what to do with other types of level 1 predictors, and as well as to segue with what Jonathan is doing in the world of Bayes. So you will get to hear that from both of us next week. But this week, let's see. Oh, yeah, one last thing. I moved homework 8 as your last homework. It was going to be due the last week of classes. I decided, what the hey, I'll give you an extra week, because why not, right? So it's due at the end of finals, as well as if you're missing any other assignments, they're due at the end of finals. I don't think anyone is at this point, but just get everything done by the end of the week and you'll be good to go. So I'm not planning on having office hours during finals week, but if you have homework questions, you can send me an email, and if necessary, we can schedule a time to talk about it if necessary. So, all right? Yeah, all right. So then what were we talking about last time? Do you remember? Time-invariant predictors, right? Give me all the synonyms that you know of to describe those kinds of predictors. Level 1 or level 2? 2. Time-invariant. Can you think of others? Between person, yep. That's good. I often say person level, sort of in the same vein. Level 2 is person level, is between person. Time invariant. You can think of any others? Cross-sectional, yeah, I take that. in the sense that you've only measured it once. All you have is a cross-sectional sample on that variable. So I'll take that. What are they for? What role do they play in the model? What kind of variance are they supposed to explain? Level 1 or level 2? We'll start there. If it's a level 2 predictor, what do you think goes with it? What do you think? Ninja like a ninja? What do you think? If it's a level 2 predictor, do you think it explains level 2 variance or level 1? Level 2. So what do we call level 2 variances? What are we talking about? Between person? Mm-hmm. What letter in the equation? Let me give you an example model here. U, right? What are these known as, these U terms? What are they called? It starts with an R. Random effects, right? We have in this model, we have an intercept. This is slide 16 in lecture 7B. We have an intercept here. We have a random linear time slope in this example model and a random quadratic time slope, right? And I have education as an example time-invariant level 2 predictor. And I have 3 different fixed effects related to education. So you can write this model either way. So sometimes you will see people write in the multi-level way, where they use beta placeholders to denote each source of individual effect, and each beta placeholder has an equation at level 2. Or you could just fill in for the betas directly, and that writes a single level equation or a composite equation that looks like this down here, where the terms in the first parenthesis would be beta 0, the terms in the second parenthesis that multiplies time is beta 1, and the terms in the last one that multiply time squared is beta 2. So we got education doing 3 different things here. What's the first one? What is gamma O1? It's related to the intercept. Keep talking. Yes, it's the main effect of education predicts the intercept. So gamma O1 is the expected difference in the intercept per year of education. What about gamma 1,1? What's that doing? The main effect of education on the linear slope, or what you could also refer to as education by time. Because that's really what it is. It's a cross-level interaction. It is the main effect of education when you look at the model this way, but the outcome that it's predicting is itself a slope. It's predicting a linear time slope. So this is education by time. So gamma 1,1 is the difference in the linear time slope per year of education. Similarly, gamma 2,1. What's that thing? It's the main effect of education on the quadratic slope, or what is actually a 3-way cross-level interaction of education by time by time. So gamma 2,1 is the difference in the quadratic time slope per year of education. So how do we know if these things are important? How do we think about effect size of each of these terms? Which of my variances is each of these going to predict? Let's start up here with gamma O1. If this is significant, what variance should be reduced as a result? You've got 4 to choose from. You've got E, U0, U1, or U2. U0, the one in its line, right? U0 is all the reasons why people need their own intercepts. Perhaps education is one of them. Next one, gamma 1, 1. This is education by time. It's going to explain linear time slope variance. U1 is all the reasons why people need their own linear time slopes. Maybe one of those reasons is education. Likewise, U2, all the reasons people need their own quadratic time slopes. Maybe one of them is education. If so, gamma 2, 1 matters. So when we explain each of these variances with its respective fixed effect, that is a type of R-square known as pseudo R-square. Pseudo means per variance component. So that's one way that we can think about effect size. Another way would be to think about what all of these effects of education are doing simultaneously. And just sort of answer the question, no, in general, how much variance in my original outcome is explained by education? And know that there are 3 different effects doing the explaining. If you want to know the answer to that question, that requires a different kind of R-square. There are like 8,000 kinds of R-squares. Here is another one that I find most useful to supplement pseudo R-squares. I don't think I invented it, but I don't know what else to call it other than total R-square. The idea is that you ask in your model for it to generate predicted values for every case in your data set from the model fixed effects. It will do that. You take those predicted outcomes and correlate them with the real ones. That's R. You square that correlation, you get R square. I'll say that again. Step 1, calculate model predicted outcomes for every case in the data set from the fixed effects. Take that predicted outcome column and correlate it with the real outcome. That's R. If you square that R, that's a quantity known as total R square. And it operates in the same way as R square in regression, in that you can think about it as how much of the total variance is explained by the model. So we can start with how much of the total variance is explained just by time. We can then compute the difference in R square after adding education and get a change in R square. And so that's what I want to show you today, is how to not only interpret each effect of the time-invariant predictor with significance and effect size, but also to how to interpret the set of them, to talk about more globally, what does a predictor variable do across the board? And how do I test that significance, and how do I get that effect size? So, you ready? Are we going to do this?
Yeah.
Yes. Jian Peng, I didn't hear you.
Yeah.
Are we going to do this? Yeah, we're going to do this. You've waited all semester to get some predictors, and now we're ready. So I'm in example 7. This is building on the same data that we've seen in multiple examples this semester, 6 sessions of a measure of response time in older adults. Now we're going to be examining moderators of rates of improvement in response time across these 6 sessions. And I have 2 different types of change models. I have piecewise slopes, which actually fit the data better, and then I have quadratic change, so that you have examples of what the predictors would look like in both situations. We're going to start with piecewise because it's a little bit easier to think about. So just to remember the setup for these models here, 6 sessions. I have 1 piecewise slope that goes from session 1 to 2, which I'm calling initial practice. I have another piecewise slope that goes from session 2 to 6. So it's a linear spline model, and that one I'm calling later practice. And I have both of those slopes as random effects, and as well as a random intercept as usual. I'm going to show you a series of models involving 3 different time-invariant predictors. Age at baseline, so how old they were when they participated in these 6 sessions over a 2-week period. I'm centering that at 80 years because these are older adults, and that was near the mean of this variable. Abstract reasoning is a measure of fluid intelligence that's thought to be an important covariate. And I wasn't familiar with the scale, so I centered it near the mean. So you can think of the reference point as somebody who has average fluid intelligence within the sample. A convention that I follow here is to put the centering constant at the end of the variable name. That way I always remember what 0 means when I'm referring to the effects of the model or building model implied fixed effects and estimate statements. And the third time-invariant predictor we're working with is education. And just so that I could show you an example with a categorical predictor, I cut it up. Never ever do this in life. This is just for the purposes of getting a grouping variable because this data set didn't have one. So I created 3 groups of education, less than high school to college, and then graduate level. So low, medium, and high education just for this example. So, with me so far? Okay, last but not least, this statement right here is subsetting the data. So I'm creating a brand new data set called trimmed from the previous data set, and this function where n-miss is the number missing equals 0. So what I am doing is subsetting to cases that are complete with respect to the outcome, which is the last variable here, the time variable, and then the 3 predictors. Do you remember why I'm doing that? What happens to cases with missing predictors in mixed? Where do they go? They what? They get deleted. So what I'm doing here is before I add all the predictors to the model, I'm ensuring that my sample stays constant so that I don't have a different set of people before and after adding predictors to complicate changes in model fit and effect size. Okay. So here's my first model. This is what's known as an unconditional growth model. So in publications, this is something that you would report as sort of your baseline for judging the effects of predictors. This represents as much variance as there is to be predicted in each of the growth terms. And in this case, it's intercept, slope 1, and slope 2. So these are unconditional, meaning that they are unexplained random intercept and slope variances. So I'm running this model, and I'm saving a couple of things here in order to be able to compute effect size. And I have written macro programs that that use these saved results to do these calculations for you. There is also an Excel sheet that goes with this example where the calculations are done. And there's plots as well. So, open that up. I'll let that load. So I want to point out a few features then of things that I'm saving that are extra. First, out PM. That creates a data set with a name given after the equals. So I named this pred, and then punc is my version of piecewise unconditional. Get this out of here. It's going to take your current data set and add to it extra columns for the model predicted outcome from the fixed effects, as well as standard error and stuff like that. So at this point, what fixed effects are in the model? Just time. So what I want to know is, before I go and do anything of substantive interest, how much of my total variation in this outcome over time is related to time? Just let's get that much out of the way. This data set then is then used in a correlation statement down here. So the column that gets created that has the model predicted outcome from the fixed effects is called pred by default. The original outcome is number match 3 response time here. So I'm asking for a single correlation between these two I'm then going to square that correlation, and that becomes my total R square. I am also saving this ODS statement right here, saves this table. Cov-PARMS is covariance parameter estimates. So this is the random intercept variance, associated covariances, random piecewise slope variances 1 and 2. So these numbers are my baseline for assessing pseudo R square. So this 28412, that's my random intercept variance. That's as much differences in the intercept as I have to be explained. It's like my new empty model, so to speak, but the term is unconditional growth model or unconditional model of change, something like that. Then we have my fixed effects. So you might remember these from the piecewise example that we did with these data. The intercept is when session is 1. That's what time 0 is here. So 1961 milliseconds on average to do this task the first time they try. They improve. So this is response time, so we want it to go down. They get faster by 163 milliseconds on average between sessions 1 and 2. And then from sessions 2 to 6, they improve further at a rate of 33 milliseconds a session, on average. The last table here is the results of the correlation. The correlation between the model predicted outcomes from the 2 fixed effects of time and the original outcome is a correlation of 0.193 and some change. I square that, that's total R square. So what I know is that if I try to put everything back together again, in terms of just total variance and response time over time, 4% of it was explained by the fixed effects of time. Okay, questions? Okay. So the first predictor I'm adding is baseline age. And in the world of cognitive aging, which is where I used to live as a grad student and as a postdoc, age is just one of those variables that you have to control for no matter what. If you don't have it in, someone's going to yell at you. Every field has a covariate like that, right, where you just have to throw it in or someone's going to yell at you. So age is mine. So it's going in first. That way I can say that everything else I'm going to look at is after controlling for age. So age, and note the subscripts here. Let me make this a little bigger. So everything in the level 2 model, if it has a subscript because it's a variable, such as beta 0I and age I, it's only I because it doesn't vary over time. Each person has one age. And I'm putting the centering in the equation so that people know what the reference point is. So that's why I'm putting minus 80 in here. In contrast, any variable that goes in the level 1 model gets a TI, because if it goes in level 1, it's per time per occasion. Do you remember the subscripts? So let me ask, let's see, who wants to play? Harry, you're going to play. You're going to play. It's going to be fun. Tell me why this is gamma 01. What does the O refer to? The O, the 0 as the first subscript. The main effect, but more specifically, what is this term gamma 01 predicting? You can phone a friend too. Okay, she's thrown it to you. Question is, why is this gamma 01? What's the O for?
O is for the intercept.
Because it's beta 0. So the first place in the subscript keeps track of which beta at level 1 you're talking about. And then why is it 1?
It's like within the intercept, yeah, the intercept predictor.
Yes, it's the first predictor in the level 2 model for the intercept. So that means if I have another one, it would be what? O2, exactly. And, okay, now I'm throwing it back to you, Harry. Harry like Harry Potter. Okay, gamma 2, 1. Tell me why this is 2, 1 right here.
It's like quadratic.
Mm-hmm. And what beta number is quadratic here? Mm-hmm. Which beta is it? Beta 2. That's right. That's why this is 2. And why is the second subscript 1? You want to throw someone else?
Yeah.
Okay, your turn. Tell me why this is 1.
The first predictor.
Yes, first predictor of beta 2. So if I got another one, what would it be? 2, 2. Very good. So now, let's mix and match. The way that you write the predictors in mixed is not multi-level. It's single level, which is why I show the composite equation too. So age 80 all by itself. Which gamma fixed effect does that correspond to in the equation? Intercept. This is age by itself is gamma 01. How about age 80 by slope 1, 2? What's that? That's 1, 1. And that means age 80 by slope 2, 6. Gamma 2, 1. Yep. So you write out the model as phrased as main effects and interactions. It doesn't matter which you write first. It will figure out that age 80 by slope 1, 2 is the same thing as slope 1, 2 by age 80. So I'm saving a column of predicted values again in a new data set. So I'm calling it pred, P for piecewise, and then the model for age. I'm saving the covariance parameters so that I can do pseudo R-square to compare models. And I'm also requesting another piece of output here. Do you remember what these contrasts do? They do lots of things, but in this case, it's a multivariate wall test. It's the idea of testing more than one fixed effect at the same time. So I'm going to get a specific p-value for each of the 3 effects of age. I also want to know that as a set, did adding age to the model, those 3 effects, help? Does age as a whole account for more variance than just time? And so this is a 3 degree of freedom F test that will tell me that. It is the same thing conceptually as asking for a test of the R-squared change back in the world of regression. It's the same thing. Then I'm asking for some additional simple slopes to help me understand the interaction terms. So in the 2 interactions that we have, age by each of the time slopes, I can talk about them as how the slope depends on age. That interpretation of with age as the moderator goes with these 4 statements here. So I'm asking for simple slopes implied by the interaction. What is slope 1, 2 if somebody is age 80? That's the one that's given to me directly by the model, is the simple effect of slope 1, 2. Likewise, I'm asking for what slope 1, 2 would be if age were 90. And so I'm filling in a value of 10 for the moderator in the interaction term here, since age is centered at 80. Doing the same thing for slope 2, 6, just swapping out those 2 variables. So I can find out for any age whether that type of person is predicted to improve significantly or not. Does that make sense? Now, the other way to think about the interaction is with time as the moderator, and to talk about how the effective age depends on what session it is. So these estimates get me the model predicted effective age at each occasion, where the first one is the one that's given to us as the simple mean effective age by the model. That's when both slopes are 0. That's the effective age on the intercept. And then I'm filling in the time values that I used to create the slopes to get the prediction at each subsequent session. So stare at that for a minute. Make sure it makes sense. Okay. Are you ready to see it? Do you have any questions about the setup before we dive into the results? Okay. So here are the new covariance parameters. Random effects, variances, and covariances. We're going to look at those in the context of an R-squared table in just a minute, so I'll skip that for here. And let's focus on the solution for fixed effects. And note that I have some interpretation questions here that we can use to go through these. Okay. First three terms. Before, in cross-sectional model land, we talked about the intercept as my reference person. Remember we talked about somebody who was age 85 and grip 9 and a man who didn't have dementia, etc. Now, same idea, but these three lines that I have highlighted here, this is my reference growth model, growth curve, so to speak, even though there's no curves. It's my reference trajectory. Given that age is the only variable in the model, and because it is entered as a main effect, this intercept of 1966 is the expected response time at time 0, session 1, for somebody who's 80. Likewise, because age interacts with slope 1, 2, slope 1, 2, this minus 164, that's the rate of change between sessions 1 and 2 for an 80-year-old. Likewise, because age interacts with slope 2, 6, this minus 33 is the rate of change per session for an 80-year-old. So it's a reference trajectory. I think the most intuitive way to interpret the effects of age is to talk about what each effective age does to that reference trajectory. So let's look at them one by one. So I've highlighted the intercept and I've highlighted the main effective age, because the main effective age, its job is to modify the intercept. So what does it do? Would anyone like to put this, we'll call this 30, this coefficient. And the sentence always starts with for every, right? So for every 1 unit change in x. Okay, wait, what's x? Age. So for every year of age, what happens? Response time at session 1, that's my intercept specifically, is predicted to decrease by 30 milliseconds per year of age. So older people, or it's predicted to increase, excuse me, this is positive coefficient. So older people start out slower. Not unheard of, right? They start out 30 milliseconds slower, higher response time per year of age. Now, is that significant? This is an easy one. Yes, am I allowed to stare at this p-value? Yes, I can, because age The slope for age has a null hypothesis of 0, which is perfectly reasonable, so a two-sided sampling distribution, this Wald test makes sense to me, so we're good to go. So yes, older people start out significantly slower by 30 milliseconds a year. Okay, got that. Now it's time for practice with more positive, more negative, less negative. Let's start with slope 1, 2, and talk about what age does to it. So slope 1, 2 is the rate of change between 1 and 2 for an 80-year-old. According to the interaction with age, what happens to slope 1, 2 as age increases? More negative. So for every year of age, this slope for the rate of change becomes more negative by 7 milliseconds. Every year of age. So older people improve faster. More negative is good in this case. Every year older you are, your rate of improvement is higher because the slope is more negative by 7 milliseconds. However, p-value says, so I would say that age makes this slope non-significantly more negative. And then last but not least, slope 2, 6. Minus 33 is the rate of change per session for an 80-year-old. What does the interaction with age say happens to it?
Less negative.
Less negative?
More negative, sorry.
More, yes, more. So it's the same pattern. For every year older you are, your rate of change between sessions 2 and 6 becomes greater, more negative, by 1.3 milliseconds, non-significantly.
So in this case, do you eventually keep the slope intact with age in the model?
Ah, great question. The answer, I think, depends on whether your intention is to say that you controlled for age, as this being a covariate that someone's going to yell at you about, or if your intention is to build the most parsimonious model possible. Because you're right, we probably don't need these two interactions. However, if I get rid of them, can I say I controlled for age? Without these interactions, I have controlled the intercept for age, but I have not controlled the slopes. Now, the lack of significance suggests I don't need to control the slopes. But if I want to keep people from yelling at me, and I want to keep the model symmetric in terms of what the predictors are doing, I would leave them in. Okay, so let's say that you decide to take them out. These are non-significant, so I'm going to take them out and move on. And now reviewer 3 is reading your paper, and they say, hey, you don't have enough power to detect these interactions, and that's why they're non-significant. Uh-oh. What do I do now? How do you...
Just put it back.
Put it back. Well, no, but if I want to make an inference, right? If I have some theory about aging, and my theory says that age shouldn't matter in people's rates of improvement, right? And I'm using this as evidence to support my theory, and they're saying, no, you don't have enough power. It's not that your theory is right, it's that you don't have enough power to test it. How do I rebut that? Rebut? Rebut. Rebut, right? Rebut?
Refute.
Refute, that's what I'm thinking of. Thank you. It's rebut or refute. I just made up a new one. Rebut. No wonder I did so well on the GRE. How do I rebut that?
Do you need to do the power analysis?
Yeah, power analysis. What are they looking for? They're looking to say that I have a big effect size, I just didn't have enough power to find it. So I need to give them some kind of effect size estimate to go with this, right? What are my choices? Let's go up to the model again. We're talking about these two fixed effects right here, gamma 1, 1 and 2, 1. What kind of effect size could I provide to describe those? R square of some kind. Which kind? Pseudo, yeah. I can look at how much variance was explained by each of these. So let's do that. Let's do that first, and then we'll go back to the rest of the estimate statements. So I'm looking at the bottom of page 4 here. This is a macro that I wrote that takes the two tables from two models that you reference. And so the covariance parameters table from the unconditional model is the cov fewer. That means the model that has fewer parameters. And then cov more is the new model that we just ran that has age in it. And the macro takes those two tables of estimates, strips out the covariances, stacks them on top of each other, and then uses a lag function to compute the differences. So this last column here gives you the pseudo R square. So for instance, the unconditional model with no predictors of the intercept had an intercept variance of 284 or whatever. It went down to 254 whatever. 284 whatever minus 254 whatever divided by 284 whatever is a reduction of about 11%. So which of my three fixed effects is responsible for that 11% reduction in the intercept? Which of my fixed effects of age is responsible for an 11% reduction in the random intercept variance? Gamma 0, 1, the main effect. And as you recall, that one was actually significant. So putting that together, yes, older people started out significantly slower, and that effective age, that main effective age, explained 11% of all the reasons why people needed different intercepts. So people who are older starting out slower is 11% of the reasons why people need different intercepts. And that's significant. So because that main effective age is significant, I know that this R square is greater than 0.
Can you do just the z-test on R square?
No. These z's refer to the test of whether these variance components are different than 0. So you can just ignore those completely. Now back to reviewer 3. %2 and less than 1%. Age explained less than 2% of the slope 1-2 variance. Not significant. Age explained less than 1% of the slope 2-6 variance. Not significant. Dear reviewer 3, we apologize that we did not provide sufficient effect sizes for you to judge the importance of our findings. As now described on page 11, these age by slope interactions were non-significant and accounted for 2% and 1% of their slope variances respectively. We do not view these effect sizes as practically meaningful, and therefore it's not a power problem, it's an effect size problem. Suck it. Now what about the last one here? What's the last line referring to? Any guesses? What other type of variance haven't we talked about yet? Residual at level 1. R squared of 0. Is that surprising? No, because age isn't a level 1 variable. Level 1 residual variance is, why are you off your line today? It can't be because of age, because you were that old every day. So then that's the mapping of individual fixed effects of age. Let me put them, come back, Mr. Mouse. There we go. The mapping of these 3 individual effects of age to each of their respective pseudo R-squares. But now if I want to talk about age more globally, right? How important is age? How much variance do we explain by including effects of age? That's a multivariate hypothesis in the sense that it's more than one fixed effect that I'm talking about simultaneously. The answer to that question is right above it. This contrasts. Contrast is the multivariate weld test that we asked for that's testing simultaneously whether the 3 age fixed effects are different than 0. Think of it as an omnibus effect of age. So we have 3 degrees of freedom. If we take numerator degrees of freedom times f, you get to chi-square. So you can report an f or a chi-square. Doesn't matter. The difference is that f uses a reference distribution that has denominator degrees of freedom, whereas chi-square does not. And that's why the differences exist in the p-values here. But they both point to the same conclusion. Yes, on the whole, age does have a significant omnibus effect, and the effect size for it would be given by the difference in total R squared relative to the previous model. So previously, the unconditional time model just had the 2 fixed slopes in it. That explained 4% of the total variance. All the piles put back together again. Now, after taking our new column of predicted outcomes, because now it's predicted based on age and time. That column, correlated with the actual outcomes, is correlated 0.33. Square that, it's 0.11. So now we're up to 11% of the total variance and a difference of about 7%. So we got 7% more of the total overall variance by putting in those 3 effects of age. And I know that's significant because that's what my wall test up here told me. Okay. How are we doing? So we've described the model so far talking about how the reference trajectory changes by age. The other way to spin these interactions is to talk about what happens to the effect of age as you get further and further into the study. So if my hypothesis is, does age matter? I have to answer that conditionally, right? Well, it depends. It depends on what session you're talking about. So the main effect of age, that's the intercept, right? That's session 1. At the beginning of the study, for every year older you are, you start out 30 milliseconds slower, higher. If we take that as our reference and then talk about what the interaction with slope 1, 2 does to it, what happens to that main effect of age at session 2? It is, which pattern is this? age is the reference point here. This is my effective age at session 1. The interaction with the slope says this effective age becomes what at session 2? Less positive, weaker. Not significantly, but still weaker. So now, for every year older I am, I start out 29 milliseconds faster, or slower, excuse me, but it decreases to 22 milliseconds by session 2. 29 minus 7. And some change. Likewise. So it's down to 22 milliseconds and some change. What happens to it as you go further into the study? Same pattern, less positive. The effective age is further reduced by 1.3 milliseconds per session. So if we go down here, these estimates are for the simple effective age as predicted by the model at each session. And you can see what happens. At session 1, that's the main effective age on the intercept. There's your 29. It becomes less positive by the interaction with slope 1, 2, and here's my 22. From there, it is less positive by 1.3 per session. However, look at the p-values. Is there any point in this study in which there is a non-significant predicted mean effective age? No. So I would say, yeah, being older means you're slower. It looks like there's a little bit of evidence, non-significantly, that that tendency is reduced in later sessions, but not significantly. So yeah, age matters. It matters at every session. Giving people extra practice is insufficient in eliminating the cross-sectional effective age that's there at the beginning. There, I think we got all of it now. Okay, so then what do? I'm choosing to leave all 3 effects of age in so that I can say I've controlled for age no matter what, with respect to the intercept and with respect to both the slopes. So I'm setting it aside and I'm adding a new predictor, abstract reasoning. So for the reasons we talked about, gamma O2, this is the main effective reasoning on beta 0, and it's the second predictor of beta 0, that's why it's gamma O2. Likewise for 1, 2, 2, 2. I'm adding the 3 new fixed effects to my model line here. By the way, do I need to worry about testing random effects? Should I be testing random effects of age and reasoning too? Reviewer 3 wants to know, why didn't you test random effects of age and reasoning? Does he or she, sorry, I'm being gendered, do they have a point? Or are they just a moron who's trying to look smart? So we have the fixed effects. Should we do our next model to test them as random? Do they have a point, or are they just trying to look smart? What do you think?
It's better than.
Hmm?
I mean that we don't need to.
We don't need to. So you vote they're just trying to look smart.
Yeah.
You're right. But why?
It's fixed.
It's fixed. Keep talking. Do you want to help him out, Minchin? You look like you want to say something.
I'm still thinking.
You're still thinking? That's okay. It's fixed. You're on the right track. Just, make the train keep going.
So is there the same over time?
Mm-hmm. What level of a predictor are reasoning and age? 2. How many levels are there in my model? 2. Can I have a random effect of age? Nope. Each person only has one value of age. I can't give each person their own slope through that one dot. Can't do it. When could I do it? What would I need to be able to test random effects of age or reasoning? A higher level, like old people nested in nursing homes or something like that. Then a random effect of age would be at the nursing home level, and it would say that age matters more in some facilities than others. But you can't have a random effect of a level 2 predictor in a 2-level model. And that, I wouldn't even apologize. That's a dear reviewer 3. You cannot have a random effect of a level 2 predictor in a 2-level model. And then throw in some citations like my book. And every other multi-level book in the history of the world. Any of those will be fine. So I'm adding the same things as before, outputting predicted outcomes to get total R-square, getting a wald test to supplement, a multivariate wald test to supplement the individual things, looking at the reasoning effect at each session to try and understand the interactions. And here we go. First question, conditionality. I've divided the table into the 3 sets of fixed effects. The top 3 lines, that's my reference trajectory again. Previously, it was for an 80-year-old. Now it is for an 80-year-old of average intelligence. Reasoning 22. And that is because each of those terms has age and reasoning as a predictor of it. Where the main effects predict the intercept, the interactions with each slope predict those slopes. So here are my age effects. Same pattern as before, although the numbers have changed. So the main effective age previously was 29, now it's 23. Why is that? If you had to harbor a guess? We've added reasoning. This is the logic that you learned in regression. We're controlling for the effective reasoning. The net effective age is 23 milliseconds. To the extent that reasoning and age are correlated, each of their effects is going to be different when paired together than when they're separate. Is this age effect of 23 milliseconds, though, is this conditional on time? We'll start there. It was before. Is it still conditional on time? Yes, it's specific to session 1, time 0. Is it conditional on reasoning? Not controlling for, conditional on. It is the same for different levels of reasoning, which means it's not conditional on it because what's not here that would have made it conditional? Age by reasoning. So I would say this age effect is controlling for the effect of reasoning, but it's not conditional on it. That is the age slope regardless of your level of intelligence. But it is the age slope at session 1. me see something real quick. Did I add that in the next model? I can't remember if I did that for this one. No, I didn't. Apparently I decided to be nice to you guys. Let's go up to the equation. In previous classes, when I decided I was going to be extra mean, I would add age by reasoning as the next model. If I wanted to add age by reasoning, where does it go? We'll go step by step. Does it go in level 1 or level 2? 2. Does it go on the intercept line or one of the slope lines? Intercept. What would it take for it to go on one of the slope lines also? Age by reasoning by slope. 3-way interactions, yes. I could do that. But I'm nice. I left that one out. So yes, in this case, it's just, let's see, just reasoning. So the same pattern with respect to the age effects. Older people looks like they start out slower. They change more, but non-significantly. Now, how about smarter people? Yes, I know it's not PC, but it's easier to think of it that way. Excuse me, people who tested higher in fluid intelligence. Smarter people. What happens to smarter people, according to the model? First one. Less response time. They're faster. Smarter people are faster. You're shitting me. Older people are slower and smarter people are faster? Whoa! Call the press. Significantly faster, right? There's even after controlling for age. So it's not that, well, smarter people are younger and that's why this effect is there. Nope. After controlling for age, it's still there. How about their rates of change? What happens to smarter people initially? So we're talking, here's my rate of change. What happens to smarter people's rates of change? More negative, which means that, yeah, they improve more. Yeah, non-significantly, but they improve more. That's the pattern. And the last one, what happens to their subsequent rate of change? Sessions 2 to 6. Less negative, which means they improve less. Now that might be surprising. It's significant even. But think about it. If you're already faster, you don't have as much room to improve. So it's not surprising that people who are already doing well don't have as strong of an improvement.
Does it provide any legitimate evidence for the program, like to select people? I mean, like I'm not sure whether it's legal to do that, but like because for smarter people, they actually do not get much benefit.
Mm-hmm.
So from the program, like efficiency, I don't know, like if the resources is limited, do they have the argument to support that? I want those resources to go to like less reasoned people instead of like smart people. You can go
Sure. I mean, you think of those as people who with sort of special needs need more resources? Yes. Whether that's ethical, I don't know. I mean, this is all observational, correlational data, right? So all the things you learned about design are still in effect here. But yeah, that is kind of what it looks like. They are improving. Like I could test sort of what is the slope at each level of reasoning, and they are improving. They're just not as improving as much as somebody who's doing worse to begin with. Whether they still benefit from the treatment is a separate question. And if you wanted to know that, you could compute regions of significance. You could find the level of reasoning at which the slope becomes non-significant. How smart do you have to be before practice doesn't help you? So we did regions of significance in the cross-sectional examples, and they're in Chapter 7 as well. And if we go the other way, one last thing here before we're wrapping up. Reasoning effect is minus 27. What happens to it between sessions 1 and 2? Starting with the minus 27 is the slope of interest. This is the effect of being smarter. What happens to that effect between session 1 and session 2? More negative, right? Bigger. Anytime you have a more, that means bigger. Less means smaller. Non-significant. From there, what happens to the effect of reasoning between sessions 2 and 6? Less negative. It's reduced. So the simple slopes down below give the model predicted reasoning slope at each session. And you can see the pattern. We start at minus 27. It gets more negative initially, but then less negative by about 3 milliseconds per session. And look what happens to the p-values. Does reasoning always matter as predicted by this model? It's heading towards not mattering. The last slope is sort of borderline here. So the extent to which being smart benefits you is reduced with more practice. And that is actually a beautiful sentiment to end on, because that is why my homeworks have like 1,000 questions. Because the effect of being smart is reduced with more practice. You practice enough, you will be brilliant. Perfect practice makes perfect, as my husband is fond of saying. So you get a chance to practice all of this stuff in homework 8. Hooray, right? That one is building on homework 5, so you'll do quadratic models in that, and that's what we're going to talk about next time, so you'll be ready to rock that. So anytime you have an interaction, it's a good idea to make a picture. Here's my picture. So I am describing what the trajectories look like as predicted by the model for people with different levels of reasoning. I picked plus or minus 1 standard deviation, where a standard deviation was roughly 5. So the boxes in the middle, that's my reference growth trajectory. And you can see that people who are smarter, reasoning 27 is the triangles, start out faster. They change more initially, but then they change less as time goes on, so that things are narrowing. If you want to think about the effect of reasoning, think about the distance between these lines over time. It's biggest at session 2, and it diminishes over time. So when you're talking about more negative, having a visual like this will help. More negative means stronger, it means better in this case. And my effect sizes then. Reasoning picked up another 5% of the intercept variance as a main effect. This one's actually negative. Slope 2 variance went up. Yes, that can happen. Reported as 0. And slope 2.6 variance, that was the other significant interaction, was explained 7%. So 7% of the reasons why people improved differentially between sessions 2 and 6 is because of reasoning. On the whole, we picked up another 5% of the total variation put back together again is given by total R squared. So we're up to 16% of all the variation in response time is due to time, age, and reasoning. Ta-da. So, questions? No? Okay. Then that's all we have for today. I will see you on Thursday. Let me know if you run into any questions with homework 7. Otherwise, go out and enjoy the lovely weather. Think about your theme songs.